This is called the histone code. It's only been worked out over the last 20 years or so. It's called the histone code. So DNA, the DNA in our genomes that's not being transcribed by RNA polymerase, you'll find that that DNA has no acetyl groups attached to the histone H3 and H4 tails, and there are methyl groups attached to the lysine residues on histone H3 lysine 9. In contrast, for the DNA that's actively transcribed by RNA polymerase, the histone tails of histone H3 and H4 have acetyl groups, as I just described. And instead of a methyl group being on lysine 9 of histone 3, the methyl group is on lysine 4 of histone 3. Doesn't seem like a lot, but apparently it's meaningful at the molecular level, all right? Does anybody have a question? All right, so this is the overall scheme of DNA packing, how the cell manages to pack our entire genome into a small space of the nucleus, and yet how segments of the genome can be accessed by RNA polymerase to transcribe RNA and generate protein. Okay? All right. What I also want to point out, excuse me, let's go back. All right, what I want to point out also is the structure of the chromosome. This of course is a metaphase chromosome, and when we talked about it the other day, I pointed out that chromosomes have a very distinctive structure called a centromere. Chromosomes have a very distinctive structure called a centromere. The centromere on a chromosome is actually what binds to kinetochore microtubules during mitosis. Remember that? It's the kinetochore forms over the centromere, and it's the kinetochore microtubules bind to the kinetochore that forms over the centromere. I want to spend a little bit of time talking about what is now known about centromere structure. And most of what is known about centromere structure is not coming from studies on our own centromeres, which are very complex and difficult to unravel.